All right, now let's answer this second question. How big does the sample have to be to get the sort of range down to up or down by 1% instead of like the 2.5% or so that we had before? So this is not a Minitab thing. This is basically just a computation by hand. So in order to, we know that for a 95% confidence interval, you're 1.96 copies of the standard deviation from the mean. And so 1.96 times the standard deviation, we have a formula for the standard deviation. It is the square root of p times 1 minus p over n. So our proportion who voted for Bob Casey is 909 over 1619. And 1 minus that, the proportion who did not vote for Bob Casey, if you do 1619 minus 909, you get 710. Okay, so that's 1 minus 909 over 1619, and the number in our sample is 1619. And so we take our standard deviation, take 1.96 copies of the standard deviation. That's how far you have to go above and below the mean to get 95%. Now, we wanted that to be 1% above and below the mean, the mean from our sample. Okay. So, well, actually, like if we compute that, that comes out to a specific number, and it's not 1%. This comes out to about 2.5%. We would like it to be 1% by changing the number in the sample. Okay, so I'm going to replace that with an n. Now, if we did poll a much bigger sample, the proportion that voted for Casey would surely change, possibly a lot, but at least a little. But I'm going to keep these numbers that I had from the earlier question in for the p and the 1 minus p, because even if they're going to change as you increase the size of the sample and poll more people, they're not going to change a huge amount. Like they should be an okay approximation of where you'll end up as you get bigger. And approximation, that's okay. We have to put some number in there. And this is going to give us a pretty good idea of how big we need n to be in order to get our approximation within 1% of the real answer, at least with 95% confidence. Okay, so I am going to try to isolate my n here. So let's take this 0.01, divide the 1.96 over to the right side, and then we need to get rid of the square root, so we'll square both sides of this. Whoops. And then we'll flip everything over. And so n divided by this stuff is equal to this thing, but upside down. Okay, 1.96 on the top and 0.01 on the bottom. Okay, so we flip both the fractions over, and then we just have to multiply these two things over to the right side. So my n is equal to 1.96 over 0.01 quantity squared, and then times my p and 1 minus p. Now, you could probably turn this into a formula, and I think that it might actually be in the book where like there might be some formula like this in the book that helps you find, this is the error you want. You need a number up here which is going to be 1.96 for a 95% confidence interval, and 2.576 for a 99% confidence interval. You have that ratio squared, and then you have times p times 1 minus p. So let's figure out what that gives us. Okay. I need some kind of calculator here. Why don't I bring up Desmos? Do I have Desmos available? Yeah. Okay, so what did we have? We had 1.96 divided by 0.01 quantity squared times 909 divided by 1619 times 710 divided by 1619. Okay, double check, 909, I think that's all right. Okay, so this is giving me 9458.9. So I guess we have to do more than that. You know, the bigger your sample, the higher your accuracy. So we'd probably have to crank that up to 9459 in order to be sure. So back to Word. So this was, whoops, 9458.9. So we need sample size n to be greater or equal to 9459 to get accuracy within 1%. Now, there's another thing that you could do to adjust for the fact that we are using these proportions that come from the old poll and their approximations. See, these numbers could change, and that could change the number down here. And there's sort of a maximum that number could come out, and that's basically if these two numbers are 1/2. So if these two numbers are both 1/2, that like if these approximations are wrong and they change as you increase the size of the sample to get closer to the real answer, whatever this product comes out to is never going to be bigger than the version that has 1/2 times 1/2. That's just sort of like the most efficient product of two numbers, where this is p and this is 1 minus p. You know, if you graph it, it has like it's a parabola with a maximum at 1/2. So wherever this ends up, whatever these two numbers are, these p and 1 minus p, this final computation is never going. The biggest it can possibly get is 9,604. So to be on the safe side, we probably should just use this number, the 9,604, and then we know that if our guesses here are not exactly right, we still have enough. So even better, use the version of n that has 1/2 plugged in there. And then you know that it's going to be enough no matter what the true proportion ends up being in the end. So that was 96/4. Okay. So yeah, this is probably the better number to use, but this one's okay too. They're both close. They're close to each other. There's not that much difference. All right. So that's basically the one example I had for today. I do want to make another video attached to today's lesson, though, to talk about the quizzes. So in the first week of class online, we didn't have any quizzes. And in this second week and through the rest of the semester, I want to bring quizzes back into that. So we'll start a new video and explain what the plan is.